We are continuing our 2.2 and 2.3, our equation solving. So we did a couple of examples, a few examples last time with some, 2 and 3 step equations here. So we're going to continue. We're going to maybe add a few more steps into the process. And we're also in this video going to come across a couple of what I would call our special cases. So let's take a look at this equation. 5 plus 3 times the quantity of y plus 2. Nope, y minus 2 is what I wanted. Actually, it probably wouldn't matter, but I'll just go with what I had written down. Is equal to, and on the right-hand side, 4y minus the quantity of 2 plus y. All right, so again, first things we want to do is to simplify each side down, treat it like a little mini simplification problem. Remember, don't make the common mistake to think, oh, I can just say 5 plus 3 is 8, and then I'm going to distribute through the 8 and make it 8y minus 16. So remember, that is not okay. You're kind of going out of order of operations there. So first thing we want to get rid of is parentheses, and the only way to do that is to distribute. So we have to distribute through this 3, in essence taking care of this multiplication before we would do any addition with that 5 that's sitting out there. And kind of the same thing over here on the right-hand side. We have this implied negative 1 that has to be distributed through to get rid of the parentheses on the right. So we now have 5 plus 3y minus 6 on the left. And on the right, 4y minus 2 minus y. All right, now again, before we start, thinking about moving terms from one side to the other, we really want to take that time to simplify each side down. So there's still more simplifying to do here. So kind of forget about right now the fact that this is even an equation and just sort of observe that you have some like terms here. On the left-hand side, you have a couple of plain numbers that you can combine. So a 5 and a minus 6 together can combine and give us a negative 1 here when we combine those like terms. So just treating that like a little, 2.1 problem there. So on the left-hand side, we have our negative 1 plus 3y. And on the right-hand side, we also have some like terms. I can combine my 4y and my minus y, and all together that's going to give me 4y minus 1y will give me a 3y. So on the right hand side, combining those like terms, I now have 3y and a minus 2. Okay, so each side is simplified now. But now if I'm at this point where I have, I'll even rewrite this as 3y minus 1 equals 3y minus 2. So let's think about this for a second. If I tried to get my y terms together on one side, that would involve, right now, if it's an implied plus 3y, it would mean subtracting 3y from both sides. Well, that means I lose my y term. 3y minus 3y is 0 on the right, and 3y minus 3y is 0 on the left. So all I would have would be negative 1 on the left and negative 2 on the right. Okay, so kind of two issues. Like, I lost my variable I'm trying to solve for, and the statement that I have left is nonsense. Okay, so what we want to observe here is that the variable, I'll say, dropped out, it disappeared, and what is left, this statement, what's left, this is very clearly false. Negative 1 is not equal to negative 2. So when that happens, when the variable term drops out and what is left is a false statement, this is going to mean your equation has no solution. And you can either just say no solution, or this is sometimes called a contradiction. I kind of just like no solution personally, but you should see the other vocabulary. So it's a contradictory statement basically that's happening there. All right, so on the next page, on the bottom of page 7, we're going to summarize these special cases. But for right now, just noting if the variable terms drop out and what is left is a false statement, that means there's no solution. Because anything I sub in on the left would have ultimately simplified to 3y minus 1. Anything I sub in on the right would simplify to 3 times that same value minus 2. And so basically, when those y terms are gone, you're going to end up with -1 and then -2, and those two aren't equal. So that's one of our really important special cases. All right, let's take a look at another example. So number 5, suppose we have 8x minus 4 times the quantity of x minus 3 is equal to 5x minus the quantity of x minus 3 plus 9. All right, so let's jump in with our simplifying. So on the left-hand side, I definitely have a minus, a negative with that 4 that I need to distribute. On the right-hand side, my first step to get rid of that set of parentheses, again, will be to distribute. In this case, the minus, the implied -1 there. So on the left-hand side, I have 8x minus 4x, and being careful, multiplying those two negatives is going to give me plus 12. On the right-hand side, I have 5x minus x, or if you prefer, minus 1x, plus 3, multiplying those two negatives, and then the plus 9. Again, there's still more simplifying that can occur. So you want to, again, continue your simplification ideas here. So on the left-hand side, just like in 2.1, we continue to simplify, and we get it down here to 8x minus 4x is going to be 4x when we combine those like terms. So those were my like terms being combined there. So 4x plus 12. On the right-hand side, looking at my like terms, I again have some x terms there. So I have a 5x and a minus 1x. So notice this is kind of using a different color here to highlight, because it's a separate problem at this point on the right-hand side in my simplifying idea. So I'm not combining them with the ones on the left. Right now I'm just treating the right-hand side like its own mini problem. So 5x minus x gives me a 4x. And then combining, I also have some plain numbers that I can combine on the right. So I have my 9 and my 3 here, both positive. So I can combine those, and I'm going to have a plus 12 there. All right, so here's what we have. We have 4x plus 12 equals 4x plus 12. So there's an aspect of this that looks similar to the last example, where you might say, oh, it looks like those variables are going to drop out again. But this time, what is left is a true statement. So if I was to continue, kind of like I did in the last problem, and I tried to get my x terms on the same side, they again, yes, they would drop out, but what is left is a true statement. So here's the deal. Whenever you recognize that the left-hand side, which we are going to abbreviate from this point forward, LHS, so whenever you recognize that the left-hand side is equal to the right-hand side, which again I'm going to just abbreviate as RHS. Now, you might have noticed it a little earlier. Maybe you didn't notice it until you got to the 12 equals 12. But whenever you notice that the left-hand side is equal to the exact same thing as on the right-hand side, this is going to tell us something different. In this case, no matter what I sub in for x, I'm going to simplify it and get the same thing on the left that I do on the right. So this is a situation where we get an infinite number of solutions. In particular, this is where we end up with our solution being all real numbers. Basically, anything works. You can sub in anything for x and it would work. So yeah, it could still be that when the variables drop out, but this time what is left is a true statement. So if we were going to kind of compare that with what we wrote up here, variables dropped out, but this time this was a true statement. So if we notice here, yeah, the variable term did kind of drop out, okay, but this time, I won't say but here, but I'll say and, kind of contrasting it with the last example, and what's left here is a true statement. So that's how we can contrast it with the no solution case. All right, so let us summarize these two situations. Oh, the other aspect of this, let's also put down, all real numbers is perfectly fine as an answer. Another way you might see this one expressed is this might be called the identity solution. So you might see that as well. All right, so that no solution, so that was the first example that we did on the bottom of page 6 there. So that occurs when, so we're just going to kind of summarize what we already have written out, but this occurs when, I'll just say once again, kind of repeating what I already said, but when the variable drops out and what's left is a false statement. Okay, and I'll just say see example 4 that we did on page 6. Now, to contrast that, there's kind of two ways you can look at this. So you could look at it in the same way. You could say, all right, what does this have in common? So once again, for this all real numbers or the identity solution, yeah, once again, we lose our variable. The variable term drops out. But this time, to make that distinction, we would say that what's left is a true statement. But I think it's even easier to kind of just think about this one as whenever you recognize that the left-hand side is exactly equal to the right-hand side. Okay, that's when you're going to have all real numbers as your solution set. Okay, so those are our two special cases. So let's end this video here. We come back, we'll look at some more examples and eventually get into maybe some that have this happen again, but we'll get into some other situations as well.